that, turning off my video, and I will stop my voice and I will leave you discussing. Thank you, Marie.
Thank you. So hello, me too. I will just stop here sharing. So yes, good afternoon. Today I'm going to talk about the challenge for direct dark matter detection, and also what are the strategies we are currently working on to overcome those challenges. So in order to determine the challenge, we need first to understand what is dark matter and how does it interact with matter, what are the properties, and why also it's so difficult to detect it directly. So in fact, the only way we have right now to see the dark matter is by the observation of our universe. And I will talk a little bit what about the big picture. So, and this is our role in particle physics. So as a particle physicist, we study the fundamental constituent of the matter and their interaction. And as we can see here is, in fact, we are between two scales. The small scales, like at the size of the nucleus of the atom, and we have also the larger scales where we have all the structure in our universe. And what is beautiful, it's those scales, those two scales are very connected. Like for example, if we want to study the fundamental particles, we need very, very high energy that comes from the accelerator, for example, where we can study, thanks to that, the very small structure of the particles and atoms, etc. But understanding as well what is at the very low scale help us to understand also what happens in large scale and in our universe, because creating so much energy to screen those little size structure, it's like, in fact, redoing the condition that we had at our early universe. So let's focus first on the large scale. So it's, in fact, like a journey to the infinitely large, and we have even the comet Neowise. And in fact, going to a journey to infinitely large is about, in fact, really back to the Big Bang. So what happened there and how can we explain the structure that we are observing right now? So if we are going back to the Big Bang, we had a huge, huge temperature and energy. So both are very connected as well. And then after that, as much as the universe expands and cool down, we have the formation of fundamental particles, electrons, quarks, etc. And then we wait again a little bit, it's not so long. We have the formation of hydrogen atom, helium, and finally we arrive to, as much as the universe expands, we arrive to the galaxy, star formation, solar planetary system, etc., with a certain temperature. So this model is our current best theory to explain the structure we have in the universe. And by looking at really everywhere over the sky, we realize that there is things that are missing. So for example, if we are looking at galaxies and try to extract the amount of mass, for example, from our current law, gravitational laws, we observe that there is some discrepancies. So, and then this is how the dark matter enter. In fact, how all it starts with Fritz Zwicky in 1933. So he studied the Coma galaxy cluster here, and he calculated the mass of the galaxy cluster using the virial theorem. And his calculation was very surprising because he found that to have all of these galaxies putting together, we need really 400 times more mass than expected from luminosity. So he postulates that for the system to be gravitationally bound, we need an additional amount of matter, non-emitting light. And after that, it stays a little bit like that. People don't really take seriously this, but 40 years later, in fact, Vera Rubin measured the rotational curves of spiral galaxy. So we have a galaxy here, and star rotating around the galaxy feels two forces, the gravitational force and the centripetal force. At the equilibrium, those two forces are equal here. And this leads to a velocity here, rotational velocity, equal to our gravitational constant, the mass at a certain radius of the galaxy, over the radius. So we saw clearly here that the velocity should really decrease as 1 over r 1/2 here, should decrease if all our gravitational laws are correct. But the problem is her observation was in disagreement with the gravitational laws. So here you have the velocity as a function of the distance from the center of the galaxy and very far from the galaxy center. And you can see that we are expecting a velocity decreasing, but we are observing something that increasing or stay constant with large radius. And the only way to explain, unless we change our gravitational laws, the only way to explain that is by adding an additional amount of matter. So there is a halo around the galaxy, a halo of dark matter with a certain density, a certain velocity that we can expect to be able to explain this behavior. Now, in astrophysics, we have powerful tools to determine in another way the mass of the galaxy or galaxy cluster. And this is what we name the gravitational lensing effect. So the gravitational lensing effect, it's a tool used, and the principle is looking at the deflection of light rays created by the strong gravitational field of a massive object. And the measured distortion of the light caused by this massive object again give us really a big proof of the evidence of a non-emitting matter. And the famous example is the bullet cluster. So it's one of the best evidence of dark matter. It's in fact two clusters of galaxies here that, and we observe what happened after the collision. So all the lines here represent the line given by the gravitational lensing effect. And you can see here that the center, gravitational center here after the collision is really, seems to not to be so affected by the collision compared to in the middle where we have, we can see it from X-ray, interact the hot gases, etc., and slow down compare because of this interaction. And more, when we calculate the mass estimation given by the gravitational lensing effect and the mass distribution given by and seen by with X-ray, we observe that in fact, we calculate that the mass distribution is more than 49 times more than the distribution of the visible matter. So this, in fact, gives us three things. It gives us, first of all, it's massive. Second, it's neutral, because otherwise he would have interact also and be seen by X-ray. And it's very weakly interacting because it doesn't seem to be affected and the gravitational center is already far apart. So it's one of the strongest evidence of dark matter. for sure, we are looking at around the galaxy cluster, but we have also from our universe, we have also the cosmic microwave background, observational evidence. So it's the oldest light in the universe, and you can see here with 3 generations of satellite with increasing resolution, how from time, so Kobe was the first, after that we had WMAP, and then finally Planck, because photons contains information about the structure of our universe, early universe, when the light finally escape and arrive now, and this is the cosmic microwave background. And it's very sensitive to the matter content of the universe, and all of these anisotropies here show you that already at this early stage of the universe, anisotropies are there. But it's anisotropies, difference in temperature of microkelvin. So it's still very tiny, but it's impressive that we are able to see that. And the composition of our early universe and from the cosmic microwave background give us, in fact, that a significant amount of 27% of dark matter is needed to explain the large structure in the universe. So what we have, in fact, it gives us that we have 5%, around 5% for the visible matter, 27% about for the dark matter, and the rest, the dark energy. So we will concentrate on those two here. And what we have is the visible matter is everything that we know. So that means heavy elements, neutrinos, all the atoms, the stars, hydrogen. So it's everything we know. And the dark matter here is something that we are looking for. And one of the favorite candidates is the weakly interacting massive particle. So in fact, we have here our known physics. And in this 23%, we have this WIMP classes of particle with a certain range, and also light dark matter. So if we want to review a little bit what are the properties of this dark matter, we have, we have that the properties of the dark matter, we know that it's gravitationally interacting. It's not short-lived, so it's stable. It's not hot, it's cold, so it's not at a relativistic speed. And it's not baryonic. So it's none of the known particle of our standard model. It's something new. And these are given by the constraint from astrophysics and search for new particles that give us exactly the property. So from what we observe, this is what we have, the identity card of our dark matter. And one that we will concentrate is the WIMP. So the WIMPs here, which is the new physics, is in fact in a certain range, because all the new particles that you are looking at has some restriction of their mass. So for the WIMP in general, in fact, for the WIMPs, it's, for example, if the mass of this particle is lower than 10 keV, it's too hot. So that means it goes too fast, and it cannot explain the galaxy structure that we are observing right now. And if it's more than 100 TeV mass, it will be too much compared to the prediction of how much dark matter we should have. So this is, and for any other particles proposed, it's always like that. But you need to keep in mind that we are looking at WIMPs and light dark matter, but you have a huge range of dark matter candidates, from ZeV to 30 solar mass. So you have a really big range, but us, we will concentrate here on this one. So we have this dark matter candidate, so how we can detect it. So the WIMP detection can have, there is 3 ways to detect it. And here is a little Feynman diagram where you have here the WIMP denoted by psi, and here Q, which is particle of standard model. So depending where you put your time, you have different interactions. So either you have the annihilation of the dark matter and then create particles, or you have direct detection where you have elastic scattering here, or any scattering, and then you have a certain recoil, and finally you have the production, if you are looking at in this way. So two protons, and then you create dark matter. So this 3 way, the indirect detection, you have a series of experiments that look at for surplus of standard model particle in the universe where the dark matter should be abundant. You have via the accelerator, so if with a possibility of creation, if the energy at the center of the mass is more than the mass of the WIMP for producing it, but also very challenging. And now we will look at the direct detection and concentrate on the direct detection. So here, the experiment look at the elastic scattering on the nuclei and look for the recoil of the target nucleus. So the WIMP interact with the nucleus and give a nuclear recoil. So we are looking at this nuclear recoil, which is detectable via different channels. So via scintillation, heat, charge, etc. But as you can see, it's a very low recoil energy. And just to give you an idea, I love to give this correlation is to be able to understand what is this energy is if you take a grain of salt and you put it at 1 millimeter of the floor, the force that it will touch the ground if you let it fall, divided by 100 billion, this is the sensitivity, the energy that you want to detect. So that means is hypersensitive detector that you want to build to detect this very low recoil energy in your detector. So all experiments has their own way to detect dark matter. So here I just put a little diagram about the different channels that you can have to detect dark matter directly. So you have phonons, heat, via cryogenic bolometer, superheated liquids, via the light for liquid noble gas detector, scintillating crystal. You have also some experiments that use both channels. And you have also the charge for germanium detector, etc. So you have a lot of experiments with different channels, and those different channels is very nice because it's also something that make them also complementary. And here it's a famous picture, not update, but just to let you know that when we want to compare all our results, we are compiling the exclusion curve. So that means the cross-section of the dark matter with our target nucleus as a function of the WIMP of the mass, the WIMP mass, because we don't know. And all of these curves represent each experiment results coming from the results that we had in the detectors. And everything above these curves are excluded, and everything below, it still needs to be discovered. So here you can see that depending on your detection technique, you can be sensitive either for low WIMP mass or high WIMP mass or both. And in fact, the low WIMP mass is very, for the detector that has very low threshold energy, able to really detect very low threshold energy, and usually also with low atomic mass, like hydrogen, etc. And if you want to reach very low cross-section, so you need to increase the size of your detector. So here, depending of the techniques I put here, you have, for example, each category of detectors that can be sensitive to this parameter space that we want to still discover and see if there is a dark matter signal. But as you can see, and this is one of the challenge that I will talk about later, we have here what we name the neutrino floor. This, which is an expected background predicted by the standard model coming from neutrino, solar, atmospheric, and supernovae, which will be the irreducible background in dark matter detectors. So finally, what do we need for the direct detection? So we saw that, first of all, we have a very low recoil energy. So that means we need to have detectors able to reach low threshold detectors, low threshold. We know that the rate is also something very low. So, and also because of the nature of the interaction. So we need a very large volume detector to have the maximum probability to detect the dark matter. And finally, the background is the principal problem for all dark matter experiment and for all rare event search. So a very high purity level is needed and other things. So our enemies is all of these particles that we can detect and create a background in our detector. So in order to find strategy to overcome those challenges, which is the biggest challenge for dark matter detection, we need to have a plan. We need to first understand what makes it challenging and also figure out what we need to do in order to succeed at overcoming the challenge we are facing. So our goal is to go below the expected signal. So in the ideal case, to be able to detect the dark matter. So the problems are all the gammas, alpha, neutron, electron, anything, for example, coming from muons and associated shower, cosmogenic activation in detector material, all the natural uranium, thorium, potassium, all the anthropogenic krypton-85, argon-39, and other. And finally, also radon, which is one of the biggest contamination and daughters for all detectors. And finally, ultimately, it's the solar, atmospheric, and supernovae neutrinos. So the cosmic background, one of the challenge, the strategy is to go underground. So we have a certain flux of muon coming from the cosmic rays, and those muons create neutrons, muon-induced neutrons in our detector, and we don't want neutrons because neutrons mimic also a WIMP signal. So we are going underground, and you can see here, as much as you go underground, here is as a function of the depth, in kilometer water equivalent, you see that this muon flux decrease and decrease. So here, just as an example, we have, for example, LNGS. So LNGS in Italy, which is the Laboratorio Nazionale del Gran Sasso, with a coverage, rock coverage from the mountains about 1.4 kilometers. And it's where there is xenon 1 ton inside, borexino, Gerda. And it's located in the region of Abruzzo here. You have also LSM in France, the Laboratoire Souterrain de Modane, with a rock coverage from the mountain of 2.9 kilometers, so much more chilled for the detectors. It's here in Modane, very close to the border from France and Italy. It is in France. It is in France. And finally, the one that you probably know, I hope, it's SNOLAB. SNOLAB, which is one of the deepest underground laboratory, 2 kilometers underground. And also what makes it also one of the best lab is it's an entire clean room inside where you put your detector. So this is compared to LNGS and LSM, it's a clean room where you have all the experiment, PICO, DEEP, MUSG, Super CDMS installed. So this muons is the problem. It's a problem for all dark matter experiment and for all experiment who want to detect a rare signal. And just to mention, in fact, at UofA, we are working on the muon propagation simulation from surface to underground. So my student William is working on having efficient numerical methods to propagate the cosmic muon, because the evolution of the cosmic rays is very important to know in order to calculate the muon flux at the surface. And this is, in fact, we use the MCQ, which is a matrix cascade equation. And then we use the results of the MCQ as an input for the Monte Carlo code proposal, which is a propagator for optimal precision and optimal speed for all leptons to propagate the muons through the rock. And you can see here what we have preliminary, because we are still working on it, but if you have a muon from the surface that comes at 0 degree underground, you can have from the surface energy 6 TeV, 6 PeV, 6 EeV, you can have the underground energy spectrum from those energy surface energy that you obtain from the surface. And in fact, again, here also a preliminary results when you compile over all the angles, energy, etc., you obtain here the underground energy spectrum from proposal and music. Here it's another simulation used in the SNO Plus paper. So, but this is important to know because underground, when they arrive, they can produce neutrons, and this is not acceptable. And that's why as well, we are constructing also around the detector passive shielding, again, external radioactivity, muons, but also all the radioactivity coming from also the rock, that can be a problem. So for example, MUSG, we have the high density polyethylene shield. For DEEP, here we have a muon veto. So you can see here there is a PMTs for the muon veto, like that we know from the Cherenkov light obtained with those muon veto photomultiplier. We know, for example, we had a muons, and it's inside a water tank. And you have also the same for example, epsilon 1 ton. So you need really to know what is entering around your detector, but it's not enough. So this is for external shield above ground and underground, but you have also to take care of this cosmic ray can create also cosmogenic activation in your detector material. So, and those spallation reaction can produce a long life isotope. So here I just show a nice picture about a copper, 10 kilogram copper, which was installed at more than 3,000 meters during 1 year, and where we can see first of all, the rate of the background of those muons, but also all the activation that we have. And it takes time for those activation to reduce. So they can be also useful for low energy calibration, the time that it decreases, and also for fiducial volume measurement, but we need also to avoid any exposure to cosmic rays, to avoid all of this background. And the strategy that we are actually also working on at SNOLAB is the production directly in an underground lab, or the storage in an underground lab. So we need to also adapt the production process to reduce exposure. So this gives a nice link to also all the expected background. So you have this cosmogenic activation background in detector material, but you have also all the natural uranium, thorium, potassium, and all the rest of those background and radon that can create also yes, background in your detector. So the strategy that we want to have is eliminate all of this source. So what do you do is doing a purification, distillation, material screening for a careful selection. And you can also have some discrimination between the main background and nuclear recoil when it's possible, if you have different channel of detection. So if you want to build the best detector ever of dark matter, it will start by doing material screening and select carefully your material with the lowest background. So you need this ultra low background. So you use high purity germanium detectors, mass spectroscopy, radon emanation facility. So the best is to perform all of this measurement underground. And SNOLAB has really a nice low counting room where you can perform all of those measurements. And so the strategy when you do a material screening is, okay, you have a certain activity coming from those measurements. Then you can carefully select the material, so taking the better and with the lowest radioactivity. You can also compare, take this activity and simulate how many events, background per year, you will use. Is it acceptable in your detector? So there is a lot of steps. And it's also useful for the final detector design, for example. So as an example, for the scintillating bubble chamber that we are building, in fact, we are working on a new design for the camera because we realized that the camera has an activity very high and too high for our detector. So you can see here is the chamber. And here is the viewport where normally the camera were supposed to sit. But in fact, we are working on the new optic design to have the camera outside or further the active liquid, which will be here. So there is a lot of information that you can extract from material screening. Now, if your activity is also too high, you can say, what will be the best way? Maybe purifying. And this is also what we are doing, which is another challenge is, okay, no, I need to use that. And I cannot find any other material. So I need to purify them or find techniques to purify those materials. So first of all, a detector fabrication assembly will always take place in a clean room to avoid any exposition to air or contaminants. Techniques also are developed for purifying, for example, the active gas or liquid or crystals. So you have, for example, distillation for krypton, 85, argon 69, and also fluorocarbon. So for example, xenons 1 ton was one of the pioneers for having a very nice distillation for krypton. We have also ARIA project in Sardinia here for depleted argon-39. And also, so all of these things for the active liquid, but you need also to develop technique for cleaning critical part. So for example, everything with ultrasonic bath, acid etching process, for example, the electropolish and electroplating techniques for the copper, for example. And you have also inside your gas or liquid, oxygen and water contamination. So you need to look at with filters. So for example, gas clean filters installed to remove that, and also getters and a circulation system to have the cleanest gas. But this is one thing so this is one of the main challenge, but one of the main and most challenge is the radon. So the radon, it's a noble gas. That means it has a very good diffusion. It can go everywhere. It is everywhere because it comes from uranium, thorium trace, and they are everywhere. It's radioactive, it's not stable, and it's threefold in nature: radon 222, radon 220, radon 219, and it has many radioactive daughters. So we need to find various ways and effective way to remove this radon. So we are exploring radon trap with carboxane or other materials, distillation techniques as well, multi-stage or stripping column. But this is the common challenge for all rare event search. So at UofA, for example, one of the strategies, in fact, in USG experiment, we want to remove oxygen water in the gas because it reduces a lot our signal amplification. So we installed a getter filter and a circulation system is used to remove the contaminants. But the problem is the getter is diffusing a lot of radon inside itself, and it cannot be used without having something to remove the radon from that. So we are exploring, here you can see students at the University of Alberta, Patrick and Freya, working on radon removal techniques by using carboxane and other material to trap the radon, but also without trapping the gas. So this is also another challenge. I'm also working on distillation techniques. So distillation is nice because you can use the volatility of the different gas and find the good range where you can separate them, because by comparing the volatility, it can be I can have it in a gas phase or in a liquid phase, etc. And this is what we name for a multi-stage distillation column. So here you can see a preliminary design where you have the Maccabi-Thierry model, which describe a multi-stage column distillation. And we have also exploring the stripping column. So at the moment, we are building a model because it's a common challenge for every experiment. We are creating a model where we can, if you put the condition of your detector, you put pressure, temperature requirement, flow, etc. From the model, you can obtain, okay, what is your cooling and heating power required to remove radon efficiently from the gas you are using? What is the reduction factor of radon you can reach with those cooling and heating power? what is the number of stage of your column? And finally, what should be the height of your column to remove a radon? And we are doing this for the multi-stage, but also for the stripping column. And if there is any student interested, I have an open PhD position for working on the model and developing and building the column. But it will be very, yes, very important for the future. And my last challenge background that I want to talk about is ultimately the solar, atmospheric, and supernovae neutrinos. So this coherent neutrino scattering that you can see here will be the background for all dark matter experiment, because there is at the moment no way to discriminate between dark matter and the neutrino floor, because they are creating nuclear recoil similar to the WIMP. So there is still a strategy to an exploration of methods to discriminate between neutrino background and dark matter candidate. In fact, is by using the fact that we have a privileged position in the galaxy as a function of the sun and how we rotate around the galaxy, that it creates a kind of headwind of WIMP blowing opposite to our direction of motion through the galaxy. And this wind will come from the Cygnus constellation, and the neutrino, for example, from the sun will come from the sun. So it's two different directions. So having a detector, a large detector with the ability of having a directionality channel will be a huge step for being sure that we can detect dark matter. So I talk about some of strategies that we are exploring. So in fact, with superheated liquids, on the simulation side about the nucleation process, there is some hint about in the bubble growth formation that there is a dependence of the particle direction. So here you can see at the very early stage of a particle that comes from this direction here, but it can come also the other direction. We can really see that at the first stage, but the time is very, very short. So this is very challenging to keep track of that. But because after 5 nanoseconds, we lose information, and it's already spherical. So if we are able to reach those sensitivity with either fast camera or acoustic sensor that are able to pick up those frequencies. So this is something that I am working currently with my group. And there is also a new idea. It's also adding an electric field to the scintillating bubble chamber. So here you can see like preliminary. So we are just looking at, okay, is it possible to create, here is a cut of the detector where you can see here is the fiducial volume, and where we create an electric field here with copper wires around and aim to have an electric field uniform and where we can keep enough fiducial volume. And finally, also with NewsG, there is a possibility that also we are exploring is thanks to the new sensor, the Akinos, where you put a certain voltage. If you are able to separate between all of these pins, you can be able to eventually use some directionality information and also low gas pressure. So you see, we have a lot of challenge for dark matter detection, and also some also challenge in the strategy. But we can also go very deeper because we have now ultra sensitive detector. So that means we have now we can see backgrounds that we were not able to see. So for example, we are seeing very rare process in our detector. So there is a lot of very interesting physics that we can extract from those detectors. Also, a better understanding of the scintillation process and the new effect that still need to be calibrated. The nucleation process in superheated liquids, for example, and the new process. So there is really a new door open as well for exciting physics. And in fact, there is a phrase that I like the more you know you don't know, because there is, in fact, it's always a world where you can always discover something, and this is, yes, like magic. So next generation of detector, we need larger detector with lower background. So we are going toward the ton scales. And I just talked to you with all the challenge that we have and all of these detector are currently facing. But we are passing through. So we have the Pico 500 liters, so from 40 to 500, Muse G as well. And we have all the liquid Nobel detector and towards ton scale. So with LZ 7 ton, Xenon N ton, 6 ton, Panda X 4 ton, and Dark Side 20K 23 ton. So we are really, yes, for me at the beginning of a new era for particle. I sincerely think that there is a really either discovery of WIMP or other dark matter or new physics, or understanding better how all of this physics process works. So yes, the future for dark matter is big, very low threshold, and pass through all of this challenge. Now the new challenge for these very big detectors are the expected background need to be known very well. So we are doing extensive calibration and simulation to understand better the detector. Very high purification as well is needed, very low rate. And finally, neutrino floor with research development to add the directionality channel. So there is a lot of R&D program at UofA with a lot of possibilities. So just do not hesitate to reach me, and yes, and I will finish by saying, because it's a challenge, once we accept our limits, we can go beyond them. Albert Einstein. Thank you very much for your attention.
Thank you, Marie, a lot. So, are there any questions? Pierre.
Hello. Thank you for the talk. It was a very nice, nice presentation. I have a question about your scintillation bubble chamber. I don't know. Do you know what to expect with the electric field you're adding to that?
So for now, the electric field will be good for example, because the scintillation light, especially for electron recoil, can be very, yes, exploit to have maybe a potential of directionality. If we have an alternate field, this is something still that we need to figure out, but I have the impression that by adding this, we can have, for example, one of the idea is if you have a bubble formation, you will have a bubble in the liquid, and a first scintillation coming from the liquid. And if you accelerate your electrons, you can maybe have another signal in the bubble. gas. But let's see.
Thank you. I just have how to say, it's not feeling, but it's about what it could do, especially how the charge could move inside the gas and the interface of the gas and the liquid, which is itself by itself moving.
Mm-hmm. Yes, there is a lot of things to take into in consideration for this, but yes, like at least for the first bubble chamber were with electric field, for example, and this is something that yes, we want to explore as well.
Thank you.
So while waiting for other hands to be raised, I have a question about you. You showed the muon spectrum from music and from the other things that you are doing, and
yeah,
they have a different. I mean, like, the discrepancy in the spectrum at low. Yeah.
yes.
So what? Yeah. So.
Yes,
The physics that is different, proposal and music. I never heard about proposal, so I'm sorry.
No problem. In fact, proposal is, yes, it's in fact is a propagator used with ice cube. So they use that, yes, a lot with, yes, the ice cube experiment. And it's really, it's really a precise method. And we would like to explore this, and especially, yes, as you can see, low energy, but again, it is preliminary. It's preliminary results. But we are able to, yes, to reach this sensitivity here, but at take, yes.
Are there, Pierre?
Hello again. What is the size of a distillation column you want to build?
The size?
Or the height, the length?
Mm-hmm. So in fact, at the moment we are, in fact, yes, I will just go back there. So in fact, it depends really of how much, yes, you can separate the radon with any gas species. So for example, with the C2F8, where we did extensive calculation, it doesn't work to have multi-stage. En fait, it works, but we need huge cooling and heating power. And the size was about, I think, 2 meters, something like that. So it's not so huge. And you can always, now we are creating the model for another one, the stripping column. So where instead of having cooling and heating power, we use gas to remove radon directly from our active liquid or gas. So it really depends, but the model is creating this for you. And you can play, for example, the heating and cooling power. You can play by, for example, the condition of pressure that you want to have, or also the flow. So a lot of parameter is taking into account. But this, we are working on that, and our goal, like for the muon propagation, our goal is to create the model and make it everything available, like that people, if they want to build a distillation column or stripping column, they have already something like to build that, and for the muon propagation as well, to know the rate in their detector.
What about isotopic separation?
So this is, we can as well. So But the problem with isotopics, it's very much more challenging, because when you build a distillation column, you need to have the volatility. So that means the vapor pressure for each species that you have, and knowing for a certain isotope what is pressure, temperature, and it can be very close to the original one. So that can be very challenging for isotopic. Yeah.
Thank you.
You're welcome.
So for argon and xenon, do you expect that this method to be, for example, better than charcoal to remove radon?
Yes, for argon, yes, the argon can be, and we have a nice example with also deep. But for xenon, it's a little bit more challenging, because the xenon and radon has a similar size property. So if you use something to decrease and slow down radon compared with the flux of the flow of your gas or something like that, you trapped as well xenon. So the radon trap with a carboxane or like usual carbon, it can be challenging. So we are exploring other possibilities of radon trap. So for example, using the separation with charge, like kind of electrophoresis things. So we are exploring various methods for that.
Thank you.
You're welcome.
Are there other questions?
Oops.
Okay, so if no other question, let's thanks Marie-Cécile again.
Thank you.
Thank you very much.